boa tarde. Hoje temos... today we have the pleasure to receive Professor Chiaki Kobayashi. She did her PhD in Tokyo. Then she had positions in Germany at the Max Planck Institute for Astrophysics, and then at the Australian National University, where we almost overlapped. I was about leaving and you were arriving. But Chiaki is now a professor at the University of Hertfordshire. She's one of the leading experts on galactic chemical evolution, especially using chemodynamics. And so recently she was awarded the George Darwin Lecture from the Royal Astronomical Society. So it's I hope you all enjoy this talk, where she will try to explain from the very beginning this history of cosmic enrichment. Okay, Chiaki.
Thank you. It's working great. Thanks very much, Jorge, for the introduction. I have been enjoying Brazil for more than a week already. Last week there was a wonderful conference in Paraty. Had a lot of caipirinha already. It's been really great. I have to go back, unfortunately, tomorrow, but I will be here all day today, and I'm very much looking forward to talking with you more. I also heard there are a few undergrad students as well in this room, so I'm going to start with a very easy background, particularly on the nucleosynthesis side, and then I will also talk a bit about the Milky Way simulation. This is a simulation of Milky Way, not the real one, but a computer simulation, and also galactic scale cosmological simulation as well. So just brief history of the universe. The universe has started 13.8 billion years ago from the Big Bang. And then initially the universe is rapidly expanded, and the very first light we can observe is a cosmic microwave background. That's soon after the Big Bang. And after that, there was nothing for a while until the first stars formed. We don't know exactly what was the first stars yet, but it should form sometime after that. Then, thank you. Then more and more stars formed in the galaxy. Galaxy also merged together following hierarchical clustering of galaxies, and then changing the shape, getting larger and larger, more massive and more massive, and then large scale structure is formed by now. And then we were formed just 5 billion years ago. The solar system is formed. And now we made the satellite and look back through the universe. So if we look farther away, we are looking at the universe in the past. So from the analysis of this very first light cosmic microwave background, we know we actually don't know much. 70% of dark energy, which we have no idea. 26% of dark matter, maybe some particle, some particle physicists try to identify it, and the normal matters are only 5%. And then my interest is even smaller component, only 0.07% of heavy elements from carbon and heavier elements. That's also called metals in astronomy. So that very beginning of the universe, even during the epoch of cosmic microwave background, we don't have heavy elements there. And then during the Big Bang nucleon synthesis, only hydrogen, helium, lithium, beryllium, boron can be formed. The reason is there are no stable nuclei with the mass number A equal 5 and 8. That's a bit of details. So because of this reason, heavier elements were not produced at the beginning. This is a Gaia taken image. This is a real image of the Milky Way. However, we are living inside the Milky Way. We can't take this shot at once. the satellite measure where stars exist, and then this is plotted on this diagram. So Milky Way, I'm going to talk about later. There is a central concentration called bulge. Two types of disks, thin and thick disk. I'm not very good at using the pointer, but anyway, you can guess. And then also diffuse component above halo component. And then there are a bunch of about 60 satellite galaxies as well, and streams. It is a big question for the Milky Way science, how these substructures have been formed across cosmic time. And another thing is, I said, heavy elements, carbon and heavier elements called metals are produced stars. The reason is to form carbon, we have to have a special nuclear reaction. It's called the triple alpha reaction. So alpha is a helium nucleus. Its mass number is number 4. And if you add the 3 of them, it becomes mass number A equal to 12. That's carbon. So you have to have 3-body reaction. That's why the universe cannot do the 3-body reaction at the beginning. Only stars can do that. That's why we are made of the stellar dust. So in the Milky Way, we have a beautiful data set now, Milky Way and the satellite galaxies. So thanks to the Gaia satellite mission, that European Space Agency built this special spacecraft to measure the motion of 1 billion stars very accurately. Plus, we have a new technique called astroseismology to estimate the age of detailed ages of stars, individual stars, by various combining with observational data. And then finally, with the follow-up observation from ground-based, making a special instrument, multi-object spectrograph, and then people have been trying to measure the detailed elemental abundance from this into European for 1 million stars, many of them. So I just listed a bunch of multi-object spectrograph projects, the past one, and also those planned phase 1. I know the Brazil is playing a really big role to develop these and also bring this field forward. The colored ones are those I have highlighted. So DR4, sorry, the slide was a bit old, but the DR4, Hermes DR4 happened a month ago. Okay. PFS is another instrument I've been intensively working these days, and Brazil also a big partner. The big survey, both for Galactic, also extra Galactic survey, will start February next year. So that's 8-meter telescope. We'll have 2,000 fiber at once. So that's going to be really big data set is coming. Having said that, if we really would like to understand the origin of elements, including heaviest one, uranium, this is actually not enough. So we have to have a target survey of extremely metal stars with very high resolution, and particularly in the UV area. CUBE is a very good instrument to do that, and again, Brazil also involved in that. So I am going to talk about chemical evolution galaxies quite a lot in my talk. Just this is only one equation I'm going to show you here. That there is a numerical way to calculate evolution of element abundance following the galaxy evolution. So the element abundance in the gas phase, time evolution of that increase if there is an ejection of metals from stellar side, stellar winds, supernova or binary system like type 1a, supernova or neutron star mergers. So, and then if stars formed from gas cloud, enriched gas, this metal goes from gas to stars. So this quantity, there is a negative quantity here for proportional to the star formation rate. And then if there is a flow, gas flow, inflow or outflow to the system, this elemental abundance also changes. The very first term depends on, most importantly, nuclear synthesis years. That I'm going to talk more about it later. plus you have to know how many massive stars exist. That's, in other words, initial mass function. And then binary physics, particularly if you want to count the rate of type 1a supernova neutron star mergers. And most importantly, all of these nuclear sensors, it depends on nuclear reaction rates. Some of them are measured in the experiment on the Earth. So this area is called the nuclear astrophysics, and then there has been a long-term, very good collaboration among them. And I've been working with my close collaborators, Amanda Caracas. She has visited here with me about 10 years ago, 8 years ago. And then the middle one is Maria Lugaro. So we have been working in this field quite a long time. The last three terms are galactic terms, I called. There are various ways to solve them. The very simple one is so-called one-zone model. So in this case, this star formation rate, inflow, outflow are given as an analytic formula under the assumption of instantaneous mixing approximation of the system you are going to calculate. There is a semi-analytic models to include the growth of galaxies in a cosmological picture, but I'm going to jump onto the most complicated one, which is solving the hydrodynamics to follow the growth of galaxies. So in this case, chemical enrichment, this equation will be applied to the location by location or particle by particle. And in that case, we can predict the internal structure of heavy elements in detail. There are various ways to do that, to solve this hydrodynamics to the large scale, cosmological volume, megaparsec volume, or zoom into the smaller area, focusing the formation of Milky Way. So I'm going to show the both sides later in this talk. So before I talk about the galaxies, I think maybe useful to explain a bit more about what stars are doing. So that's the basic. This is again very easy slide for many of you. The life of stars heavily depends on the mass of stars. This is simplified world, only single star here. The low mass stars don't do anything, just hydrogen stays hydrogen, while the sun, like stars like the sun, start forming helium in the core, and then this nuclear energy is the luminosity source of many stars. The sun will ignite helium at the center later on, and to form carbon and oxygen core in the end. And then the solar type star don't do anything further. Outer envelope will be released by stellar winds, forming beautiful planetary nebulae later on, and the central part will become white dwarf. If it's single star, white dwarf don't do anything. But if they are in a binary story, will be a bit different. So more massive stars, the stars more than 8 solar mass or so, the carbon and oxygen core start fusing carbon and oxygen. So it's for oxygen and neon magnesium core. So this core can become unstable and then suddenly explode as supernova. But this process is called electron capture supernova, slightly different type. More standard supernova explosion happened stars more than 10 solar mass or so. In this case, the oxygen neon magnesium core becomes silicon core, and at the very center, the iron core is produced. So iron is one of the most stable elements. Therefore, once the iron core is formed, it's almost not possible to form heavier elements than that. Instead, if iron is in the very center of stars, it's lose pressure, and that's trigger the gravitational collapse. And this is the standard one. You often see the massive star end with core collapse supernova. This is the channel, iron core exploding core collapse supernova. After that, probably the stars up to 20 solar mass or so will form neutron star in the center, while a massive star will probably form black hole. So this or statement, or neutron star or black hole, this is still not well understood yet. And then people try to constrain this more in detail. So JWST is useful not only for very distant galaxies, but also this nearby stellar object as well. So here is a beautiful image of a famous planetary nebula. In a near-infrared camera, you can see this beautiful the mass loss around the central star here. But the JWST is sensitive to even longer mid-infrared area. And then with this infrared, this is the same planetary nebulae, but you see something different in the center. There is a second star also here. So this is known from other observational results, but the JWST really show this clearly. This planetary nebulae is actually a binary star made of white dwarf and then normal star. So I mentioned already, if white dwarf is in a binary system, they can do something very special thing. But it has to be in a good binary system. Not all white dwarf in binary system can do that, but if they are in a good binary system, white dwarf receives some mass accretion from companion star, and then white dwarf increase the mass, reach Chandrasekhar mass, and then boom, just explode as a type 1a supernova. So this is a very classic model for type 1a supernova, and also very good channel to produce particular element. Manganese is this is the only way to enhance manganese relative to iron. But there are a number of problems observationally, particularly the number estimated may not be enough if you follow the binary evolution as well. So the other channel has also been proposed. One of the other channel is sub-Chandrasekhar mass explosion. For example, if there are two white dwarfs here and then merge each other, so in this case, it's possible to have some iron as well, maybe slightly lighter element, but not very much manganese. But both look, observationally, both look similar type 1a supernova. Just nuclear synthesis signature will be different. So just the massive star, I said the type 2 supernova, the standard one will happen if stars are more massive than 10 solar mass or so. So in 1987, in Magellan Cloud, there was a bright spot appeared, and then people in the southern hemisphere enjoy the bright spot for a month or so by naked eye. That's so nice story. I've never seen planetary nebula. Many people have never seen the supernova explosion, but that was a very lucky moment. And then recently, JWST also took the very central image of this famous 1987A planet, the supernova. And then the central component, there is a strong argon emission. And by analyzing these argon emissions, it is actually confirmed that the central part is a neutron star. Otherwise, this strong signature, very ionized argon cannot be explained. So the stellar evolution theorists keep saying, after supernova explosion, neutron star should be formed. And then this is confirmed now, thanks to JWST. Okay, so this normal supernova explosion happens only probably up to 20 solar mass or so. We know this by analyzing nearby supernova. So we can't see by eye, but with the telescope, it's possible to measure how bright are they, taking the evolution of luminosity on the left panel, or even taking the spectra. Anyway, complicated story in short, from a combination of these two observational results, it's possible to estimate what was the mass, progenitor mass, and how much energy is produced, and how much iron is produced. So this figure is showing the results. Below 20 solar mass or so, ejected energy is 10 to the 51 L, exactly the same energy estimated for 1987A in previous diagram. But above that, probably more massive star producing more energy and more iron. So we found this and named it hypernova. So this is the same quark-wrap supernova channel, but more energetic and producing more iron. So how frequently this happens, we don't know. But in a chemical evolution point of view, I have some suggestion. It should be quite a large fraction of massive stars should go into this hypernova explosion. There may be no failed one as well. So these green points not producing enough energy and ion, and these are called failed supernova. It's not supernova, it's failed and don't do nothing, probably just forming a black hole. So this is also some, the rest of hypernova will probably go to this failed supernova. So normal supernova explosion observed as type 2 supernova happens only up to 20 solar mass or so. So after the stellar evolution code, following the nuclear synthesis, there is an onion-like structure already introduced. Central part is the ion core. So this is an onion structure, very smooth hydrostatic phase. But during supernova explosion, more explosive nuclear synthesis happens around the center. And that's the phase, interesting heavy elements are created. Depending on the layer, intermediate area is forming cobalt, chromium, and a bit of manganese as well. While in the very central part, will produce zinc and cobalt. So measuring all of these are ion peak elements, but taking the detailed ratio of these ion peak elements, it's possible to study what happens in the very central part, particularly how much material goes to neutron star or black hole can be studied by measuring this zinc and cobalt. So this central part behavior is not well studied. There is a model for that, but this is very uncertain area. Okay, so I said iron is one of the most stable elements, but on the Earth there are heavier elements, particularly important one like precious element, silver, gold. And then the nuclear power plant is using this iron, that's uranium, is a heaviest stable element. And I heard that here the astronomy students also have taken the nuclear physics course. So this is the most important figure of nuclear physics, showing the stable nuclei with a black line plotted against the number of neutrons and number of protons. So very light element up to from hydrogen to iron, there is a 1-to-1 slope, meaning in the nuclei there are equal number of neutrons and protons. So that happened up to iron, oxygen as well, the same 8 and N. While heavier than that, you see the line is tilted toward more neutron-rich side. So there must be neutron capturing process. That's called neutron capture process. Blue lines are called slow neutron capture process. This is a process to capture neutron on the time scale of beta decays. And we know this happens in quite a lot of stars, in low mass stars, during asymptotic giant branch phase. But this blue one can reach only up to here, doesn't reach to this island. To reach this uranium thorium island, it's necessary to assemble a neutron much more quickly. So that's the second channel called rapid neutron capture elements, called R process. You should collect neutrons much more quickly. An obvious place where you can find the neutron a lot. The obvious place is neutron star. Neutron star is a star made of neutrons. There must be a lot of neutrons. So if neutron star, if you have 2 neutron stars, then merge them, probably something exotic happens. That have been proposed long time ago, half-century ago. Neutron star merger is one of the sites. And the another site is maybe during the massive star explosion, during Qualcomm supernova, it's also possible to do something. So this happens much more quickly, much shorter time scale than beta decay time scale. So to form the heaviest one, uranium, thorium, or actinide, so this is a very difficult process. europium is relatively light one. Europium is easier to form, but actinoid is harder. So neutron star merger was thought to be the channel, maybe possible, but the rate may be not so high. And then I'm also suggesting this one, the rare type of quark over supernova from a massive star becomes hypernova type explosion with jet. It's possible to see neutron-rich ejecta. So this is a computer simulation, and then with a special initial condition with strong magnetic field and rotation, we see the matter becomes neutron-rich, and actinoids can be produced. So this is my preferred site for this actinoid production. The another one proposed one is a collapser. So collapser is not a supernova. It's similar, but a collapser is collapsing, a black hole forming. But around the black hole, there is an accretion disk. And then some people says that this accretion disk can be neutron-rich and then can form actinoids. But some other simulation people says, this material does not become so neutron-rich. So this is debated side. In any case, difference is collapser is not a supernova, so they don't produce ion. They may produce just actinoids only. So I think many of you have seen this our version periodic table. I already said I think almost all here, but in a different diagram here. So in a periodic table, I'm showing summarizing each element come from where. So I already said light elements come from Big Bang nucleosynthesis. That's black out already. Loma star, like the sun, can produce half of carbon, 75% of nitrogen, the S process, barium and lead. While quark collapse supernova include electron capture supernova, that's Loma-sen, magnetorotational supernova, that's Hyma-sen, include O-ring them. The blue appears everywhere. So that's very important site for most of the elements. Type 1a supernova is the merging or the accretion of white dwarf, mainly producing these ion peak elements, particularly manganese. The neutron star mergers are finally included, but you can see the contribution is very small. This was a surprise. Since then, I've been working on more about neutron star mergers, closely working with the people who are calculating binaries. Binary physics is very complicated. It's not very well understood yet. And it is possible to increase the rate, event rate of these neutron star mergers, or the nuclear physics may be slightly different depending on the mass of a compact object. It could be very different in the case of neutron star black hole merger instead of neutron star neutron star. So this is included in the latest model. In that case, it's maybe possible to explain observed europium abundance near the solar abundance only with neutron star merger. That's a black line. But if you see this black line doesn't stay constant and it's sharply decrease at lower metallicity. So at lower metallicity for extremely metal poor stars, something else, quark supernova is still necessary. So the neutron star merger contribution will be higher, but not fully explain everything. And quark supernova, namely magnetorotational supernova, are still needed. The LIGO and future mission like LISA will measure the mass of compact object if they have that merging event. So this was very exciting happened in 2017 when the first neutron star merger was detected. That's JWST 17, that's the one. And then we thought that we're going to see this neutron star merger many more in coming years. But actually, not so many. There is one more case, neutron star merger reported in 2019. But since then, we haven't heard. We have heard about the neutron star black hole merger, 2 cases in 2020. That's the only robust detection of these compact object mergers that could produce R process elements. Among them, the astronomical transient called kilonova is detected only one case. That's another concern. We see neutron star system merging, but we don't actually see explosion afterwards. So I already said this, there must be out-process production from quark-clock supernova. And in that case, it's similar to hypernova. They could also produce iron and other elements as well. So I kept saying this, and then went to the Australia with my close friend David Young here in the picture. Also, Jorge is also a very close friend of him as well. And then he said, hang on, I have a very interesting star in my sky mapper survey. And then we looked at this elemental abundance pattern. This is exactly what I wanted to see. Here there is it's very metal poor star, FeOH minus 3.5, extremely metal poor. But even though it's a very clear detection of uranium and thorium, here is a beautiful standard R process pattern is here. And then surprisingly, the strong detection of zinc and high abundance of nitrogen. So all of these are pointing out, so this enrichment source, this is a single enrichment source producing not only actinoids, but also zinc and iron peak elements. Probably outskirt was rotating, producing nitrogen. So this hypernova magnetorotational supernova scenario works very well for this case. The other model is neutron star merger plus some chemical evolution. That might be okay, but it's not as good as this single enrichment scenario. So I think this is a very clear example that a quark-clock supernova, at least some small number fraction of quark-clock supernova is producing the heaviest elements. How much time do I have? Okay, so I don't have so much time. I knew this is going to happen, but the rest is not very much. I just run through how simulation can do to follow the galaxy evolution as well. So this I already mentioned. I've been working on hydrodynamics combining to chemical enrichment. So what I am doing is I'm finding cooling gas and form new star particle. The star particle is not a single star, it's a still massive association of stars. So I assume initial mass function to the star particle, and then follow, after that is the same, following the stellar winds, quark-clock supernova, and type 1a supernova neutron star merger, and then remnant black hole neutron star white dwarf remain. So this is what's happening in the Milky Way simulation. Later, I will show more massive star evolution. So in that case, some fraction of cold gas should go into the black hole suddenly. About 1,000 solar mass also, this is a parameter. And then we follow the growth of this massive black hole into supermassive black hole, following the accretion of gas and then merging with other black holes. So these merging of supermassive black hole will also be detected by future gravitational wave mission like LISA. There are various uncertainty here. For example, we don't quite know how stars formed. It could depend on the magnetic field or many other factors. So this is a bit try and error. Plus another factor is called feedback, how the supernova explosion affect to the surrounding matter. So this process is also uncertain. And galaxy modeling, galaxy simulation people try various things to check the model by comparing observations. So here I'm showing a simple luminosity evolution of Milky Way type galaxy here. It started cosmological initial condition. Background, there is dark matter and gas as well, but I'm showing only stars here. Beyond redshift 8, already you see the bulge formed by the assembly of small gas-rich galaxies. So this is CDM, cosmological initial condition. So there are small satellite galaxies keep on accreting. It's not possible to avoid that. But I avoided major merger, otherwise I can't make Milky Way type galaxy. So later on, you see the disk component grow inside out. The disk was smaller in the past, and it's getting larger and larger. And then by this long, now disk-like structure here, and we are living around 8 kiloparsec there. There might be some debris here, like LMC, like Galaxy also exists in this one. Okay, so I already showed this last week in a parity conference, so just briefly, I can predict the metallicity map, for example, which look pretty similar to what Gaia satellite measured. So above is my simulation, the bottom is observation. This is not bad. There is a strong vertical gradient, so metallicity is highest on the plane, but becomes lower above the plane. Also, there is a radial gradient. Central part is more metal rich and becomes lower at outskirts. Elemental abundance have a very different view. So if I take a ratio between oxygen and iron, so that you see the disk plane is rather blue, meaning low alpha to iron ratio. This is also very similar to what Gaia satellite get. The Gaia also showed alpha to iron ratio is low. Oxygen is one of the alpha elements. There is a strong vertical gradient. In halo, alpha to iron becomes high, but a radial gradient is rather shallow. So that's also shown in this simulation. This simulation has a bar, so along the bar, this alpha to iron ratio becomes low, because star formation is ongoing along the bar. So the simulation, we can do many things. For example, trace back the gas flow, and then we found there are two gas flow on this galactic disk plane. One is close to the radial plane, so radial flow. This brings in the metal enhanced gas toward the center. And there is another flow happening slightly later time, is more flow coming above, bringing a relatively metal poor gas. Type 1 is occurring there, so it's more low alpha gas, low alpha to iron ratio gas is coming in. In this particular simulation, this radial, this second flow inflow happens redshift 0.3, and that's actually becomes important later on. Next question is, we can even follow a star particle one by one, where they are formed and where they are located. This is very simple question. So if you form stars in a circular orbit on the disk plane, the star particles are moving like that, the radius does not change. So if I plot birth radius on X, and then where are they now, I expect 1-to-1 correlation. So you see this trend as well, this red line. So some stars are doing just circular orbiting on the plane. Well, you see this second flow is here. So this meaning they are located, let's say, present day radius 8 kiloparsec now, like solar neighborhood, was formed inside. So that's that it could be the solar system was born at 6 kiloparsec and travel to 8 kiloparsec by now. So this on the average, the radial migration happens outgoing, and then this bringing metal enhanced star to the outer area. So metallicity radial gradient becomes flatter with this gradient effect. So in this figure, we showed how metallicity radial gradient changes as a function of time. There are various things plotted here. The red is gas gradient, which is observation similar to the observed value, like about 0.075 dex per kiloparsec, that's the number. But if we measure stellar gradient, that's slightly flatter. And this flattening is caused by the migration showed in a previous plot. Also, that there is a small gas inflow in this particular simulation that's caused steepening of the gas phase gradient that's happening. The value becomes larger in this last 3 giga-year. So this not always happens, but in this particular simulation, it's happened also. Last week, we discussed a lot alpha to ion bimodality, and then I already discussed quite intensively last week. Simulation can naturally predict this bimodality, also some low alpha sequence, and then very rapid enrichment of gas as well. It's a minor component, but some area is enriched very rapidly, and then forming low alpha metal rich star in this simulation area. I already presented this metal alpha to ion bimodality depends on the location within galaxy. This high alpha is more hot, kinematically hot star, while low alpha population belongs to more circular orbiting thin disk population. And then this is another figure I showed already last week. I can predict this elemental abundance diagram, not only for alpha to ion, but also many elements. I'm just showing the power of simulation now. This hydro simulation can include all element production, all nuclear synthesis that I discussed already, and then to predict elemental abundance in detail. This figure depends on the location within galaxy, or age of galaxy, age of stars, and so on. And in near future, this kind of simulation can be compared with detailed spectroscopic survey. Okay, I think I don't have so much time, but I just briefly touch this exciting news for high redshift galaxies, mainly with JWST. Before that, this is my now cosmological larger scale of simulation. The color is showing metallicity again. So now it's not a smooth central component appears. It's a different view. Along the filament, many things are happening. So this quite a massive satellite galaxy are created onto, oops, I want to go back. Along the filament, chemical enrichment already taking place. You will see this supernova driven, this strong gas outflow here. And this enriched matter, together with the main component, fall onto the central massive galaxy. This central massive galaxy hosts supermassive black hole as well, and that's blown away enriched gas at the very final moment in this massive galaxy evolution. So this is very complicated, but how much metals are produced in which galaxy, and how much metals have been lost in each galaxy, this can also be analyzed in the simulation. And then we found that the galaxy, on the average, gaining metals by in-fold accretion, that's already enriched gas. But the important thing is less massive galaxy lost up to 80% of produced metals by the supernova driven outflow. And a massive galaxy can lose 20% of metals by the winds driven by central supermassive black holes. So in a cosmological simulation can treat these complicated flow of metals as well as the production of metals within the galaxy. So I'm going to skip a couple of slides here and then jump onto the elemental abundance. So at high redshift, we can't measure ion abundance easily, so we have to use some other indicator. Nitrogen and oxygen both are light elements, but they can be detected with strong emission lines. So that's why now new figure is showing different elemental abundance components. The good thing is nitrogen and oxygen come from different sites on a different time scale. So it's not constant value, but it's value evolving. So we know from the local galaxy observation that the nitrogen to oxygen ratio increased toward higher metallicity. This is explained by the nitrogen yield itself depends on the metallicity of the progenitor supernova plus AGB star also producing nitrogen at a later time. And then there is a plateau phase. Nitrogen to oxygen ratio becomes constant. And this is produced, in our case, inhomogeneous enrichment from AGB star. Christina Champini is working on this as well for a long time, together with Beatrice. Observation, and then there is another interpretation as well, involving rotating massive stars. Anyway, so far, this is pre-JWST information. And I was quite happy with that until the new observation suddenly came. The story happened 2021 on a beautiful Christmas day. The JWST was launched. It was a beautiful launch. It's more successful than we could expect. A year later, the first JWST image was presented by Joe Biden, US president back then. And this is beautiful. You can see a cluster of galaxies. Many people jumped in, these little red dots. These are likely to be very distant galaxies. Or some people jumped onto this arc. These are gravitationally lensed galaxies. This is beautiful. But I've been working on stellar abundance for many years. Well, what I would like to see is not just the image, but spectra. But JWST has a very good spectra as well. It's called NARSpec. It's covering a wide range of wavelengths, covering this key emission lines, some also absorption as well, this metal produced lines from redshift 0 to out to redshift 14 or so. So by measuring these lines across cosmic time, we can do extragalactic archaeology now. The available information is limited, but we can do this in the near future. So this is the most exciting area now in this, I would say, in this extragalactic community. So this is one of the most popular spectra in extragalactic studies. It's called GNZ11. It was a candidate for very high redshift galaxies around redshift 11. JWST confirmed it. It is indeed redshift 10.6, only 430 million years after the Big Bang. So this is beautiful spectra. And then if you have a very good eye, there is something here. It's a very strong nitrogen emission line. This is very unexpected. I said the nitrogen comes from later either metal enriched supernova or AGB stars with a longer time scale. This is only very beginning, and yet nitrogen is very high. So many people jumped on these results, trying to understand this uniqueness. Maybe it may be enriched by supermassive star, the star more than 1 million solar mass, or various stories may be related to nearby globular clusters. So I'm going to skip again a few slides, and then my interpretation is different. So my interpretation is, this is not the so exotic and emitting source, but this can be explained by normal Wolf-Rayet star, massive star up to 120 solar mass or so, but it's a unique phase. So if I assume intermittent star formation as in this diagram, so that it starts from the very high value with Wolf-Rayet, but suddenly oxygen is produced by quark-gluon supernova. This nitrogen to oxygen ratio go down quickly. What I assume is up to here, there is a dilution of increase of hydrogen. So line go back to the left. And the second starburst increased nitrogen abundance by Wolf-Rayet. And then second generation of quark-gluon supernova increased oxygen. So during this, just after the second burst, this phase, it's possible to explain this very high nitrogen to oxygen ratio to be observed metallicity. So this is one interpretation, and I expect this is a rare event, but this is soon after the starburst, so maybe luminous and maybe selected better. So Subaru PFS will hunt these unusual nitrogen emitter, and estimated to be like 1,000 of them should be found in near future. That's all I think I presented prepared today. I think I talked quite a lot about origin of elements at the beginning, and then extragalactic archaeology is now, it's possible to compare simulation to observation for many elemental abundance to understand the early process as well. And then we can do the similar approach applying to extragalactic studies. That's all. Thanks very much for listening.
Questions or comments?
Hello, Chiaki. Thank you for your presentation. When you talk about failed supernovas, are you talking about that kind of supernova that when you have the collapse, everything falls into the black hole?
Every central core will go to black hole. So before the explosion, some outskirts, maybe containing a little bit CNO abundance, may be released by the wind. Mm-hmm. So the core inside the carbon oxygen core will collapse to the black hole. But there may be small production of lighter elements.
So it should be an event with a lot less emissions. Should be very hard to identify, observe that kind of events. How could we know that those are failed supernovas and have a better strategy to observe them?
So it's very difficult by definition. So the supernova is shining. We can detect them by production of iron. Iron is the source. Radioactive decay is the main energy source back then. So it's by default, the failed supernova do not produce iron at all. So we can't observe them. There may be oxygen production slightly outskirts, but anyway, it's not heated, so that it will not create a stronger emission line either. So it's very, very difficult. If it's only in indirect way is we can measure elemental abundance of stars in detail. And if we see many, for example, metal poor, the extremely iron, no iron detection, but only carbon and nitrogen is enhanced. So this could be an indication of failed supernova. We already know similar case. Faint supernova is similar, it's different. Faint is faint. Small production of iron and the carbon and nitrogen produced.
Hi, Chiaki. If I may, I could ask two questions. One was about the simulations that you showed, the nice movies. Is this solving for the chemical evolution network in each step, or is it painted particles? How you set this up? Because if it's fully self-consistent, and then would be very interesting. Are these simulations public?
Yeah, so the nuclear, it's a step by step. So nuclear physics is solved for the stellar evolution side, and the galaxy simulation takes the results of nuclear synthesis years, and the star particle evolve moving around the galaxy, distribute different elements at a different time. So this ejection, metal ejection, is solved self-consistently. The equation I showed at the beginning is solved particle by particle in my case. And then what was the second question? Sorry. So it will be public. So that I have to write a paper, but I'm enjoying caipirinha so much these days. So that's the problem. Yeah, but next year, sometime next year, so all the particle data, including all elements, will become available. But if you have a particular idea, you can come and talk to me later. Yeah.
Here.
Hi.
It was a very broad and interesting talk, and I might have several questions, but I will focus on the simulations, because you got this zooming in order to do this cosmological simulation of the past of the Milky Way, but you considered a hydrodynamical simulation, gadget simulation, and then you zoom in and got something within the 10 or 30 kiloparsec scale, right? And then you could follow the evolution of the system, considering all the feedback, even the growth of the central massive black hole. So my question is, because of course, if you have taken MAGD effect, this is very important in the inner region and in the formation of the central black hole. So this might affect the feedback, all the feedback process. So my question is related to the feedback of the AGN outflow versus the star formation wind. what would be the dominant in most of the evolution of the system, and the fact that you got that grand design, that massive stars might the feedback from starburst from star formation would be more important, and more massive more massive ones would be the AGN feedback, and the less massive ones from star formation wind, right? And in this sense, this would affect also the star formation rate, right? So how this major result compares with the, let's say, the empirical Kennicutt law of star formation. So can you?
Yeah, okay, thanks. So various things. I didn't have so much time to explain this clearly. So I showed two complete different set of simulation. One is cosmological simulation, including AGN feedback following the glass black hole. But this is a large volume simulation. The numerical resolution is not so great. So, but on the other hand, I say zoom in simulation is not just zoom in of this big volume. It's a rerun. Pick some interesting area of the initial condition and then rerun all hydrodynamics with better numerical resolution. So that in that way, nice Milky Way structure can be presented. So this is completely different around what's shown. Generally speaking, supernova feedback can eject matter, including metals, only the galaxies, total mass of galaxies less than 10 to the 10 solar mass. And if the system becomes heavier than that, supernova just energy is not enough to blow this galactic wind. This has been a long-term problem, and it was an idea that maybe AGN could help ejecting or quenching. Star formation is not happening in massive galaxy now, so AGN may be able to help that. The numerical simulation supports that. How much accurately we can solve, this is a big question, because AGN affect, it's a galactic scale outflow we are talking about, but AGN is a very tiny object. There is a naively accretion disk around the supermassive black hole. There may be magnetic field also working. So how AGN feedback we can accurately follow is a big question. I don't think we are doing a so good job yet. Another question is, Kennicutt-Schmidt law is already assumed in all simulation I showed earlier. Star formation rate is scaled to the gas density, basically. So that is assumed. But with magnetic field, maybe this assumption may not be valid. So this is another question point. I think one more thing. Yeah, supermassive black hole also grow together with the merging of other black hole. So this is not assumed, but it's also what's happening in this cosmological simulation in our case. Yeah, so not a very clear answer, but there is a tool here by changing, for example, assumption of star formation and AGN feedback, comparing observation, we might be able to get a complete picture of galaxy evolution. We are not there yet, but this is a good tool, I think.
Thank you, Chiaki, for the talk. I'm not from the field, so pardon me if the questions are too naive, but you mentioned about our processes and they being related to core collapse supernovae. But after JWST 0817 and the merger rate of neutron stars that was inferred from it, are our processes relevant in supernovae events?
So the argument we are making is neutron star merger is not enough to explain observed early process element. Hence, supernova should be producing. But we haven't seen any direct observation that a supernova is actually forming gold or platinum. People trying to look at it. So gold and platinum can have some absorption features as well. So people trying to detect that. Neutron star merger case as well. Only strontium is directly observed. It's actually not very heavy element. Again, for neutron star merger, we really like to see more direct evidence. So this area is, once this gravitational wave detection, people think, oh, this is solved, but it's actually not solved yet.
Okay, so thank you, Chiaki, again, please.